and we've become quite fond of it. And we're fairly confident that Sunday night will be a good night for us. Thank you. Now Tomas will tell you how we're going to get there on time and to the right spot.
Thanks, Adams. That's a very difficult path to follow. Curiosity is currently about 670,000 miles from Mars and is approaching the planet at a speed of just 7,800 miles per hour, not as fast as it would be when it enters Mars. Since Curiosity was launched by an Atlas V rocket back in November of last year, the navigation team has been using the tracking data from the antennas of the Deep Space Network to determine where Curiosity is and where it is going. The navigation team has designed trajectory correction maneuvers that have adjusted Curiosity's trajectory so we'll enter Mars at the right point, so it can safely and accurately be delivered to the Gale crater. The mission control team has executed so far 4 trajectory correction maneuvers, and the last one was successfully executed last Saturday evening. First image, please. Here you can see a picture of the surface of Mars. You can see the entry point in which we enter the atmosphere. So we enter at an angle of minus 15.5 degrees. And then the ground track of Curiosity as it descends into the surface of Mars and the touchdown point in the north side of the Gale crater. You can also see the ground track of the Mars Reconnaissance Orbiter as it will fly over Curiosity and provide communication support. Next image, please. Here you can see where we were going to enter the atmosphere of Mars before the maneuver that we executed last Saturday. The entry target, that was the target for that maneuver, the onboard state that we put in the spacecraft last Monday, and our latest estimate that we have calculated 3 days later. So the maneuver moved us by about 13 miles. We are now about 100 yards, 1,000 yards from the entry target. And the difference between the latest estimate of the onboard entry point, and the onboard state is just below 200 yards. The main task of the navigation teams over the next few days up to landing is to keep processing the tracking data from the Deep Space Network so we can accurately predict this entry point and, if necessary, send an update to the spacecraft. The other task is to determine any maneuvers that may be needed, but it seems that based on the results that you are seeing, we may not need to do the maneuver that was planned for tomorrow. The navigation team needs to tell Curiosity where it is as it enters the atmosphere of Mars so it can find its way to the Gale crater. There is no GPS in Mars. We have to track Curiosity from the antennas in the Deep Space Network in the Earth to tell it where it is as it approaches Mars. It is like driving to work just by looking back in the rearview mirror to the antennas of your house. Then next, Ashwin is going to tell us about the weather in Mars.
All right. So as Adam mentioned, we care about the navigation accuracy and then what weather occurs on Mars when we enter. And Tomas is delivering us right down the middle, but there's nothing I can do about the weather on Mars except predict it and then design the spacecraft to be able to handle all those potential conditions we can encounter. So that's what we've done the past few years. We're interested in understanding the weather on Mars. And we've been studying it for several years now to design a system that can tolerate pretty much everything Mars is known to come up with at this season. If we see any extreme weather in the next few days that even pushes the limits of what we designed the spacecraft to, we at least want to know it's coming so we can understand how that might affect the accuracy at which we land. So you might wonder, how do we predict the weather at Mars? Well, I'm going to turn to the live Doppler 8000. Actually, can't do that. I wish we had that on Mars, but really what we have is a spectacular weather satellite up there now. It's actually doing a lot more than measuring the weather. The Mars Reconnaissance Orbiter. So the first graphic shows the Mars Reconnaissance Orbiter doing two things. It's looking down at the surface taking both temperature measurements and taking color imagery of the surface, just similar to weather satellites would do on Earth. The temperatures in the atmosphere of Mars are related to the density, and the density, the thickness of Mars' atmosphere, is what will catch the spacecraft when we arrive at Mars. You can see also that MRO is looking ahead of itself and looking kind of at the atmosphere in its thickness, and that allows us to get very accurate temperature distributions with height, which we then turn into densities that we use to simulate our landing many thousands and thousands of times. So I'd like to show you a global weather map of Mars. But to orient you, I'd first like to show you this similar map of Earth. So this is the kind of format we'll be using in our maps of Mars, sort of unfolded, unwrapped the sphere of Earth onto this weather map of Earth, the beautiful planet. I'll draw your eye to just above Australia there, where there's a little ring, just over Indonesia. And that's exactly the same location on Mars where Gale Crater is, our landing site. So if we now go to the map of Mars, this was taken just 2 days ago by the Mars Reconnaissance Orbiter, the Mars Color Imager on that spacecraft. And it shows Gale Crater as well as some other features that we're interested in. When we arrive at Mars, it's coincidentally about August in the seasonal cycle of Mars. And that means it's just coming out of winter in the southern hemisphere, and Gale Crater is just slightly in the southern hemisphere. We expect this to be a cold time of year. It's when Mars is further away from the sun than in other times of year. And because of that, we see a lot of water ice clouds on this map. That's a good thing. We expect we've modeled and predicted from past years that Mars will be nice and cold and clear and covered with this water ice haze when we arrive. And our latest map of Mars does, in fact, show that. The thing we do worry about a little bit is our dust storms. Now, we've designed the spacecraft to be tolerant of all the dust storms that have occurred in previous years. But as I mentioned, we do want to understand if there's a chance of dust storms occurring on landing day, because they may kick up extra winds that would cause us to land a little less accurately than we've been predicting. So just to make things interesting, on this map, there is a pretty healthy-looking dust storm at the bottom of the image. It's pretty far from Gale, more than 1,000 kilometers away. But it is kicking up dust in the atmosphere that has the potential to perhaps spread over to the site. Now, we're not worried about this particular storm. It's the kind of storm that tends to disappear within a day or two. And since this map is already almost 2 days old, we expect by Saturday, when I give you the next weather update, we won't even be talking about this storm anymore. So finally, I do want to show you also this interesting image from this is a close-up image of a similar small storm that was taken in 2007. Now, these dust storms occur on Mars at this season because the polar caps are receding back as we go from winter into spring, and there's a temperature contrast between the cold CO2 frost cap and the bare ground next to it. That temperature contrast stirs up winds that raises dust and creates these local dust storms, which you can see kind of boiling from the surface. Now, this particular storm was from 2007 and lasted less than 48 hours, and that's the kind of storm we saw on the image of Mars from July 31st, and we expect it to behave the same way. The final thing I'd like to share with you is that we don't only look at the weather in the atmosphere of Mars, we also look at space weather. Space weather occurs when plasma or high-energy particles leave the sun through coronal mass ejections or solar flares. Now, if these high-energy particles come from solar flares, they can reach Mars within only about an hour or two of leaving the sun. Why do we care about these things? These high-energy particles can impact the spacecraft in two ways. They can either cause errors in the memory of the spacecraft or cause stars that aren't really there to appear on the cameras that we use to track and navigate the spacecraft. Now, the spacecraft, of course, has been designed to be very tolerant to both of these effects. But again, we just monitor the environment around the sun using spacecraft around Earth and at Mars even, so we know what's coming. And so we have a good understanding of the environment the spacecraft will be in when it performs these very tricky maneuvers on Sunday night. So with that, we'll turn it over to Doug.
Thanks, Ashwin. For about 2 years, NASA's been sharing with the public the adventures that our robotic envoys have exploring the cosmos using a tool developed here at JPL called Eyes on the Solar System. Now, thanks to some fantastic data and support from Thomas and Adam's colleagues in the EDL and navigation teams, we're able to actually show you inside your web browser exactly what Curiosity is going to be doing over the next few days. What you're seeing now is actually a live view using Eyes on the Solar System, which you can get to just by going to eyes.nasa.gov inside your browser. It needs a reasonably modern computer, a Mac or PC, a desktop or a laptop is absolutely fine. And there are two things we can do here. One is that using this predicted simulation data provided by the Curiosity team, we can show you exactly where Curiosity should be right now. In fact, as Thomas mentioned, we're about 670,000 miles from Mars and doing just under 8,000 miles an hour. And you can track this, all the time, all the way through to Sunday evening. But because we already have this data, we can hit a magic button here that says Preview. And we can fast forward through to Sunday evening and see how things are going to unfold if things go according to plan. And so here we can see the spacecraft as it approaches Mars, and you can see the landing site way up on the limb right here. And on the night, if you're using the live mode, you'll be able to watch exactly what happens right inside of you like this. But we can actually skip forward. So I'm going to skip forward through EDL, and you'll see the exact same things that you'll have seen in the animation, but now you're in charge of the camera. You can stop, go backwards, forwards, look at it from any angle you want. As I fast forward through time, get closer and closer to the landing site, you can see the values screaming off on the side there, the altitude, the velocity, the distance to the landing site. You can see those guided turns that Adam talked about as we kind of guide Curiosity to the exact spot in the surface of Mars that we want to get to. And you can see a countdown to the different events on the right-hand side. I'm going to stop just after we get to the heat shield deployment, which comes up in just a few more seconds. There goes that ballast Adam mentioned. Here comes the parachute. You can see the beautiful parachute here. And you can see the countdown just down there. For a few more seconds, we'll see the heat shield come off, so I'll skip forward just a little more. There goes the heat shield. And at any time, of course, because it's a prediction, I can pause the action. I can go and have a look around. I can say, well, actually, I want to go and look at the heat shield. And here you can see the Medley suite on the inside of the heat shield that was mentioned earlier. You can go back, look at the spacecraft behind us. And you can also see that this doesn't live in isolation. This lives in an engine that hosts the whole of the solar system. So behind us, you can see there's Mars Express. There's the Earth that's about to set about a minute after this moment in time. There's Mars Odyssey coming over the horizon. And towards the south, we can see the Mars Reconnaissance Orbiter. And if we want to look at things from over there, we double-click the mouse, and we can ride on board MRO and see that it's tracking Curiosity as it makes its way towards the surface. I can unpause the action. You can see MRO's orbiting Mars. I can go back to Curiosity. And you'll see that 20 seconds after this moment in time, the Earth sets over the horizon. I'm going to fast forward just a little bit further towards the surface until things get really exciting. And now we see the spacecraft drop out of the back shell as it makes its powered descent towards the surface. I won't show you all the way to the end. I don't want to spoil it for you, but it's very exciting. And if things go according to plan on Sunday, then what happens should be very, very similar to this prediction you see right here. Everything I've shown you can do right at home inside your computer just by going to eyes.nasa.gov. And with that, I'll hand it back to Jane.
Thank you, Doug, and thanks to all our panelists this morning. We are ready for some questions from reporters here at JPL. If you do have a question, please raise your hand and wait for the mic to come to you. And let's start here in the third row, blue shirt.
Hi, Eric Han with Nature. My question is for Tomas. So you showed us the charts showing how the latest estimate was about 1,000 yards off from the intended target entry.
Right.
Does that mean that the center of the landing ellipse has shifted by that amount? And if you could also say what you'll use to decide whether or not that's too much and you need to correct for that in this window to do the correction maneuver tomorrow.
Want to take this on?
Sure. Because of the guided entry that we spoke about, errors in delivery of the spacecraft, like that 1,000 yards that we have, can be flown out by Curiosity on our way in. As long as accurately as Curiosity knows her location, she can control to some fair degree down to very accurately on the surface. So that 1,000 yards, if we were to choose not to correct it, we'll just let Curiosity correct it once she hits the atmosphere.
Would you have to upload that software?
Nope. She knows where she knows the target that she's going to on Mars. And all that we have to do is give her our best estimate of where she is currently. And she'll do the rest as she flies through the atmosphere.
Okay, we've got a question there in the second row.
Hi, Irene Qualtz with Reuters. Just to follow that up, what's the range then that the rover can correct for? And when would you be deciding if a TCM was necessary tomorrow?
So we've established a TCM criteria that's well within what her control authority is. What the range that she can clean up is tens of kilometers of error. But we would choose, very likely, if the space